Hi, this is Alex, and today we're going to do an introduction to linear equations. Let's get started. So you might be thinking, what is a linear equation? Well, it's an expression that contains an equal sign, as we can see here in our example, and two variables raised to the first power. In our case, we have x and y. Now, let's take a quick second to address our variables. It may look like they have no exponent, but just because we don't see one doesn't mean there is not one. So when we have a variable raised to the first power, it's pretty standard in math just to write that as the variable itself, instead of writing x to the first power or y to the first power. But if you have any other exponent, you would definitely want to write it. But in this case, it's okay just to leave it as y and x. And then the most important feature of a linear equation, in my opinion, is that it can be graphed to produce a straight line. And a way to remember that is by looking at the word itself. We have the word line that is right in there. So before we move forward, I want to talk about two terms really quick that are kind of important to either introduce or review, depending on what the case would be for you. So the first one is coefficient. So we have two different numbers here in our example. We have a 3 and a 5. The 3 would be our coefficient because it's kind of attached to the variable x here. In other words, x is being multiplied by the coefficient 3. So there, the coefficient is attached, so to speak, by multiplication. And then a constant is just a number that's off by itself. It's not attached to a variable by multiplication. It's just on its own. So that's a nice little distinction to make. And we'll also be talking about some more terms as we move along, and some of them may be new to you as well. So let's keep on moving. So this is actually the graph for the example we just talked about, and I will rewrite that equation here. And now if we take a step back and look at this equation and this graph, it seems like such a stretch, right, that equation would produce that graph. But we're going to try to break things down here in the next few moments, and you will see how nicely linear equations can be used to graph. They're a great starting point when you're learning to graph, even though it seems like such a daunting task right now. So hopefully I'll be able to make that quite easy for you. So the why question. You always want to know the answer to this, right? Why do we study math? In this particular case, why do we study linear equations? So they're really good models for certain types of real-life situations. Certainly not all of them, but we're going to have one at the very end of the lesson, which hopefully convinces you its usefulness in some respect. It goes much deeper than just that one. And it's also very useful because, as I just mentioned, linear equations are pretty easy to graph. It doesn't look like it maybe right now on the onset, but certainly they're much easier to graph than other types of equations. It doesn't mean we can't graph other types of equations. They're just a bit trickier, and this is just a great way to start learning how to graph and figuring out those basics and getting a feel for things. And another big reason why we study linear equations is to get a good feel for the concept of slope, which becomes especially important if you're going to move forward in your study of math to an advanced degree of mathematics, to a level that is a lot higher than most people go. And even if you don't do that, slope in and of itself is kind of a neat thing, and so we're going to talk about that here very soon. So one of the best ways to start this topic out is by looking at three different forms of linear equations. So unfortunately, this first one, even though it's called standard form, it's not all that exciting, but it's still worth looking at and talking about. And it's a nice review for the terms we just discussed. So if you look at the standard form here, we have ax plus by equals c, and it just looks like a bunch of variables. But actually, our a, b, and c here are actually filled in with numbers. So I'll give you an example. Let's do 3x plus 2y equals 5. And so now we see that we only have our variables x and y left raised to the first power and our equal sign. We're good to go. It's a linear equation. And this is what's called standard form. And then going back to our terminology, the 3 and the 2 would be our coefficients, right? They're attached to the variables by multiplication. And then our 5 would be the constant. Now, a little trick that we're going to talk about and use very soon is the fact that we need to have this equation solved for y to graph. Well, y is over here on this side of the equation, but with all this other stuff. And so it quickly becomes evident that it's not the easiest thing to work with. We can solve for y really quick, but this form is really hard to get to and really doesn't do much for us other than help us to find intercepts. It's a really quick way to find intercepts. And intercepts are the point where our graph crosses the x and y axis. So if we go back a couple slides to this graph for the example that we had, let's label our axes. It's very important. So our x-intercept would be where the graph crosses the x-axis here, so that would be this point. And then our y-intercept would be where the graph crosses the y-axis, which would be at this point. So again, standard form is really useful to quickly find those points if you don't know them and all you have is this. It's a great way to do that, but getting to this form again is not all that fun, although it could be solved pretty easily for y. Then we come to the most important form, which is slope-intercept form. As you can see, it's already solved for y. That's why we love it so much. And for this form and the next one, you'll notice that their name kind of gives it away. There's going to be a slope involved as well as an intercept, namely the y-intercept. So we see our variables y and x, and so when y equals mx plus b, we know that our m and our b are the parts of this form that we really care about. So I'm going to reveal our terms that we need to know. And again, slope-intercept form, there's our term slope, which is going to be our m, and that's going to be a value that's filled in, as is our intercept, our y-intercept that is, which is this value b. So there we have it. And so our slope, we're going to go a little bit more into that here in just a little bit, but I want to go talk about our y-intercept for just a minute. So we have this value, but what exactly does that mean? So let's go back again to this graph, which I've used already. So our y-intercept, if we notice here, this is where it crosses the y-axis, right? Well, let's say we had a graph that crossed down here, and a graph that crossed down here. Remember, they're all straight lines. If I can draw this other point. Maybe not. There we go. And you'll notice again, I just wanted to point this out, this line clearly is a straight line. I'm going to make sure I pointed that out. So anyways, we have different y-intercepts here. What do you notice that's in common with all these? Well, it's probably pretty evident that they all have an x value of 0, right? So the y-intercept, or I'm sorry, the y-axis is when x equals 0. So no matter what point we choose along this line, the x-coordinate in a coordinate pair would be 0. So we know that our y-intercept is going to be 0, comma, and then our y-coordinate is going to be whatever the b value is. So again, this is very useful for graphing. We're going to talk more about that and how to use this to graph here in just a little bit. But for now, let's do a quick example, just like we did for the standard form, to actually put things into perspective. So let's do 5x plus 1. So our slope, m, would be 5. So m equals 5. That's our slope. We're going to go more into that here in a few. Y-intercept is this b value, which is 1 in this case, right? And so our y-intercept specifically, we'll just call it y-int for short. Our y-intercept would be 0, because the x value is always going to be 0 along the y-axis, and the actual intercept is going to be 1. So that's a way to extract some information from this particular equation in slope-intercept form. So this is the big one, right? And for the final form, it's also very useful, and actually can be solved for y and be put into slope-intercept form, just as the standard form can. But again, we're not really going to focus on the standard form in this lesson. It's not very useful, but certainly point slope is here. So you want to definitely pay attention to this one. It comes in the form y minus y1 equals m times the quantity, which is everything inside the parentheses, x minus x1. So you see these x's and y's and then x1, y1, maybe a little bit confused. But again, let's take a look at this name here. It tells us a lot. So we have the word point and the word slope. So we're going to have a point somewhere in here, and we're going to have the slope. So we already know that slope is m, right? Slope is m. That's an eraser. It's not going to help. Slope is m, and we have our variables x and y, and then we have these weird looking things. So the one here and here, that's called a subscript. And it's just to kind of keep things in order and to make sure you don't think of these things as the variables. These are actually going to be filled in with values, and these values actually come from a point. And our point in this case is x1, y1. So it's useful for cases when you are given at least one point. We're going to call that point x1, y1. But you cannot easily graph using slope-intercept form. So of course, if it's in this form, it's going to be pretty ugly to graph, but then you can easily solve it for slope-intercept form and then go from there to graph. So if you have to put something in point-slope form, it's going to take you a little bit longer to graph, but it's definitely a helpful form to remember. And again, the only reason why we're using these subscripts is just to make it very clear which ones are the variables and which ones need to be filled in with values, which would be your x1 and y1. So again, let's take one more little example here just to make things clear. Let's say we're given the point -1, 2. So first of all, whenever you have a point with a negative value, it should throw up a red flag to you. You have to be very careful when you're plugging it in, because when you subtract a negative, you want to make sure you make that become a positive, because that's what should happen. But what often happens is that people forget to do that. That's okay. It takes some practice. So here we go. Remember, x and y stay, so we should have y minus our y1, which is going to be the y value from our point here, our coordinate pair. So y minus 2 equals m. So let's say our slope is 4. Equals 4 times the quantity x minus our x1, so the x coordinate of our coordinate pair, which would be -1. So we have minus a -1. So when we simplify this, the left side stays the same. Then we have 4 times the quantity x minus a -1, which is the same as x plus 1. Right? And so that's where you have to be a little bit careful, but it's pretty easy to plug in, right? And then, of course, going from here, if you wanted to solve, which we will eventually do, you're going to have to do some distribution over here, which we'll talk about. Since we have 4 times the quantity x plus 1, and to distribute. So, going back to slope, very important thing to talk about before moving forward, because we need to know a little bit more about slope to be able to work with it and use it to graph. And it's a really important part of graphing linear equations. So slope is a rate of change that describes how steep a line is. So with that definition in mind, looking over at this graph, would you think the blue or the red line is steeper? Hope you'd agree it's the red line, right? So that means that the red line has a larger slope, right? So think about it. If you're walking up this red line as if it were a hill, you'd have a much tougher time than if you were walking up the blue line. So that's the idea behind slope. And then one quick note about this, these are positive slopes, okay? There's also such thing as a negative slope, which would be coming downward like this. So we'll encounter one of those types of slopes a little bit later. So the definition of a slope, we see a lot of, well, not a lot, but we see some odd symbols over here, but trust me, it's not too bad. So again, we have used the letter M several times already, and that is the standard letter to describe slope. We define it as change in y over change in x. And all this part of the definition is a fancy way to say change. So this is the Greek symbol delta, which means change. And so all that's saying is change in y divided by or over change in x. So if we're looking for change, do you think we can tell that from just one point? Can we find the slope by figuring out this change from just one point? Probably not, right? So if you're trying to figure out how things have changed, you need at least, the starting point and then a point along the way to compare, right? And so, in fact, that's all we need. And that's the exact phrase right here. All we need is 2 points on a line to find its slope. Unless it's already given to us, then we shouldn't do that because it's just making us do too much work, right? And so let's call those 2 points x1, y1, x2, y2. And so again, we're just using the subscripts to keep us in line. So the ones over here just help us to know that this is point 1, whatever it is. And the subscripts of 2 over here help us to know that this is point 2, whatever it is. And just to make note of this, it doesn't matter which point you call point 1 or the other way around. If you're given 2 points, let's give some examples down here. Let's say you're given a point 1, 0, 0, 1. Those are 2 points. Doesn't matter which one you call point 1 or point 2, but whichever one you decide to call point 1, stick with it. And the same with whichever one you decide to call point 2. Stick with what you call each point, and then use that when you're plugging it into the calculation here. And so if we call this point 1, I always like to write it just to help me to remember and not get confused or messed up along the way. So if we call this point 1, this is going to be our x1, this is going to be our y1. So we would plug those right in here. And then if this is our point 2, this would be our x2, y2. We plug those in right here. And then it's just a simple calculation. So we're going to go try this here in a bit. But this is the calculation for slope if you're given 2 points. And sometimes you'll have to find the slope, or sometimes it'll be given. It just depends. But this is a good tool that you'll definitely need to know, and we can actually learn a lot from it. But before we do that, we have a couple of but wait statements. So you might not be thinking these, but I certainly am. For you guys' sake, what about our original example? So we had y equals 3x plus 5. So let's think about it. What would the change in y and x be for the slope in that equation? Well, our slope, again, would be attached to this x here, our coefficient for this equation, which is 3. So our slope, m, equals 3. So if we look back here, we're looking for change in y over change in x. Well, we don't have a fraction. Or do we? Well, we actually do. It's a nice reminder that you can divide any integer by 1. So 3 is an integer, right? And it will stay the same. That's true for any number, right? You could divide -1 by 1. It's still going to be -1. And same for 1 million divided by 1. It's still going to be 1 million. And so we can easily make this into a fraction. And this is a good little trick moving forward. And that's a good little trick in lots of different areas of math. If you can sneakily, I don't even know if that's a word, if you can change something like this in a very slick way to help you out, go for it. As long as you're not changing the value at all, you're good to go. And so I think I just defined a new word too, sneakily. So anyways, we were kind of slick about this, right? And yet we didn't change it at all. 3 is the same as 3 divided by 1. And now we have a fraction, and we can see that our change in y is a positive 3. Our change in x is a positive 1. So that's a important thing to talk about, because that is definitely going to come up. And again, that's going to be useful for when we actually start using slope. For now, you may be like, why does that matter? But we'll see here in just a moment. This is another but wait statement. What about something like the slope of this equation? So we have y equals negative 2/3 x minus 4. So our slope here, I hope you'll agree, is negative 2/3. So you may be wondering, what do we do with that negative sign? It's pesky, it's out front. I really don't know what to do. But you got to remember, a negative sign outside of a fraction can be placed either in the numerator or denominator, but you definitely don't want to put the negative sign in both at the same time, because that'll just cancel it out or get rid of it. You've got to include it, but you can choose. And we discussed earlier, it doesn't matter which point you choose as 1 or 2 or whatnot, and the same goes here. It doesn't really matter whether you put the negative sign in the numerator or the denominator. And I'm going to try to demonstrate that in one of our examples, just to prove to you you can really go either way. And so all of these statements are equivalent, which makes it very convenient for us, right? We can just choose whatever route we want to go. But we definitely want to include the negative sign in there. We're trying to figure out our change in y and our change in x. And we'll talk about this a little bit more in here in just a second. So why do we care so much about this slope? So if we think about change in y over change in x, it really helps us to graph a lot easier. And there's something that students often say, and it's rise over run. It's a nice little phrase to help us remember change in y over change in x and what it means to us when we're graphing. So rise is basically, since it's a change in y, we're figuring out what's happening to a point in the vertical direction. Is it going up? Is it going down? So if it's going up, it's going to be positive, right? If it's going down, it's going to be negative. So that's an important thing to write. So if you have a positive rise, that's going to be up. And then the run, if you have a positive run, that's going to be running to the right in the horizontal direction. And then just opposite for negative. If you have a negative rise, sounds kind of odd, that means you're going down, right? So your change in y is negative, that means you're moving downward. If your change in x, your run is negative, you're going to be going to the left instead of the right. So this may be a bit confusing now, but we are going to work through this and kind of get these ideas more solidified. So how do we graph? We have all this information. How do we put it together to help us graph? Because that is our objective, right? So first things first, you want to have a starting point. So usually this comes from your y-intercept from our slope-intercept form. So we already have a point, and we're just going to use that as our starting point. So this is just kind of an arbitrary drawing down here. So let's say that's our starting point. Then we're going to use our rise over run to find our next point. So let's say they're both positive, which means we're going to be going up and to the right. And then that is going to be our next point. So we use our rise over run, our slope, to find our second point. And then we're going to connect our starting point and the point we found from our slope with a straight line. And that's probably about as good as it's going to get. And these rise over run dots are sometimes called a slope triangle. So if we were to connect these, it would kind of look like a triangle. And that helps you at the beginning. That's a great way to visualize what's happening. But as you go along, you'll definitely want to just have your line visible. You can certainly leave the points. I think that's good. And even label them if you want to. That would be really nice. But slope triangles will definitely help you at the start to kind of visualize what's happening with your rise and your run. And I'm going to do that, I think, on probably the first example, just to give you a feel for it, and then kind of back off of that to encourage you to do the same. So we kind of have our three major points pointers rather for graphing, and we just want to follow those with this first example. So we have our equation here, which I hope you will agree is in slope-intercept form, right? We have y equals mx plus b. You may be a little bit confused about the negative though. So all that means is that our b value is actually -1, this entire value over here, okay? So again, we're going to kind of pick out the pieces that we need. So we first want to have our starting point, which is our y-intercept. It's going to be this entire value here. So our y-intercept, again, I just usually abbreviate it like so. Remember, our x value is always 0 when we have a y-intercept, and the actual intercept is -1 on the y-axis. So that's our starting point. So if we go over here, let's label our axes x, y. So our y-intercept is at 0 on the x-axis and -1 on the y. Put a little dot. There's our starting point. We've already got one task done. So now we need to take a look at our slope and use that to help us form our next point on this line, which we haven't even drawn yet, but we're getting there. So again, slope-intercept form y equals mx plus b. Here's our m. Our slope is 2. But we don't have a fraction. But remember, that shouldn't be an issue, right? We learned this little trick. 2 over 1. Right? We can divide any integer by 1 and it will remain the same. So now we have our change in y, our rise, which is 2, and our change in x, our run, which is 1. They're both positive, so we're going to be going up and to the right. So for our rise, we have up 2 units, 1, 2 from our starting point. I'm actually going to go ahead and draw the slope triangle, I think. And then we're going a run of 1 to the right 1 since it's positive from that first little rise. So you want to do rise, then run. You could also do it the other way around. Do you want to do it one at a time? Especially when you're starting out. If I could get this point drawn better, that would be fantastic. There we go. It's a little bit better. So, I guess I could switch to another color, keeping it pretty boring. But here's our slope triangle. So we have our rise and our run, and then we're just going to draw a line right through it. And there we have it. And so again, the more you do this and the more practice you get, you will want to not draw that slope triangle. But it's definitely helpful at the start. And there is our line. So again, just to reinforce, this is positive slope. The next example we see here is going to have a negative slope, and we're going to see that. So first things first, you'll notice this is actually not in slope-intercept form. It's very close, but these are kind of mixed around here, or switched around rather. So what we're going to want to do is really just swap these around. It's not too bad. I guess we'll stick with red. We're going to move this entire term over here, -3/2 x, so it's first. There's our mx, and then plus b, and our b is going to be this entire term over here, -1/2. And so now that we have it in the correct order, again, we can just get out the information we need. Start with our starting point, our y-intercept, x-coordinate's always 0. In our case, y-intercept is this entire term, -1/2. And so let's go ahead and graph that. Label our axes. Start at x equals 0. And then we go down to where y is -1/2, so it's right in between these two units. There we go. Very sensitive. So sorry about that. And then now we need to find our slope to be able to get our next point and then finish this one up. So our slope, again, just using the idea of slope-intercept form, y equals mx. So here's our m, this entire coefficient, -3/2. And So that's going to tell us one of two things. We can either, remember we have options, we can either have negative 3 over 2 or 3 over negative 2. I'm going to graph with this one first, then we're going to go back and check to show you that this one is also fine to use. They both work. And that's kind of the cool thing about math. You have a lot of different options. So if we use this one, our rise is negative, which means we're going down 3 units from our original point. So we're going to go down 1, 2, 3. It's giving me some grief today. There we go. And then we're going to go run 2 units. It's positive, so we're going to the right. So we're going to go run 1, 2. So again, this would be our slope triangle, but I'm not going to draw it this time. I'm just going to go ahead and form our line. And as I said, this is in fact a negative slope. It's going in this general direction from the top left to the bottom right instead of going from the bottom left to the top right. So this is negative slope. So this is one slope triangle. You could also again use this version of the slope. They're the same exact thing. Let me prove it to you. We start at our initial point. We rise 3 units up since it's positive. 1, 2, 3. My pen. There we go. And then we run to the left since it's negative. So 1, 2. And we end up with a different second point, but you'll notice it's on the same line as it should be. So just make note when you're deciding where to put the negative, it's going to determine which way you're going to go for your second point, whether it's to the right or to the left. So just keep that in mind. Doesn't really matter. It's kind of a neat way to show you, again, just like the different options that you have to get the same exact result. So this example, we're not asked to graph. Yay! But we are asked to find an equation. We want to find it in slope-intercept form, but we are given a point, 1, 4, and a slope of negative 2. So the first thing you should be thinking of is point-slope form. I think it's time for a different pink color. Let's do blue. So point-slope form, just to remind you, we need a point and a slope. We already have our slope, and we know that slope we call m. It's negative 2. And our point, remember, we call it x1, y1. And in our case, our point is 1, 4. So, to make it clear, our x1 is 1, and our y1 is 4. And so now we have all the components we need to put it into point-slope form. So our form again is y minus y1 equals m times the quantity x minus x1. x1. So let's start plugging in. We should only be left with x and y as our only variables. So y1 is 4. So y minus 4 equals m, which is negative 2, times the quantity of x minus x1, which is 1. In this case, we didn't have to deal with the double negative, which is nice, but now we know how to handle it, since I did mention that you should be aware whenever you have a negative coordinate, or if both of them are negative, you need to be especially careful. So for example, if this was a negative 1, this would be x plus 1 because of the double negative, but we don't have to worry about that. So Now we want to start solving for y to get in the form y equals mx plus b. That's our goal, and that's typically going to be the goal. Again, if you're given a point, it's probably going to take a little bit longer for you to get to slope-intercept form to be able to graph, but it's still a very nice form to use. It works really well. And so let's finish this thing out. So like I mentioned a while ago in the lesson, we're going to need to distribute at this point. So we need to take this -2 and distribute it to both the x and this -1. And so I always like to draw these little swoops to kind of remember what distributing is really doing. It's a nice kind of way to remember that. So we're going to bring down the y minus 4. We're not going to do anything with that yet. We're just going to take care of the distributing. So we have -2 times x, which should give us -2x. We have -2 times a -1, which should give us a +2. Let me see if I can select. No, I can't. It's okay. So we have y minus 4, -2x plus 2. Start a new page here. And finally, we want to get y by itself, as I had mentioned. So the inverse of subtraction is addition, so we're going to add 4 to both sides. Since we have an equation, we want to keep it balanced. We need to keep it balanced, actually. So whatever operation we do to one side, we have to do it to the other. And then -4 plus 4 is going to give us 0, so that essentially goes away. We're going to bring down our y, equal sign. I'm also going to bring down the -2x because you cannot add a constant to something that involves a variable. They have to be separate. You want to combine the like terms, right? So we can combine the 2 and the 4, so 2 plus 4 should give us 6. And we are finally in slope-intercept form as we were asked. So we are done. A nice way to check that we at least did one thing right is that we have a slope here of -2, and that's what they gave us in the problem. But the point of doing all this work, even though we already had the slope, was because we didn't know the y-intercepts. Now from this, we probably could have figured it out pretty easily, but going through all these steps is really nice for when things get a little bit trickier. But we know we at least got our slope right, and then this would be the y-intercept in this case. Okay. So now, we are given 2 points, and that's all we're given, and we just need to find the equation in slope-intercept form. So whenever we see a point, we should immediately think point-slope form. But our problem here is that we don't have the slope, but we do have a nice little calculation to find it when we have 2 points. And just to remind you of that calculation, it's m equals y2 minus y1, change in y, over x2 minus x1, change in x. So change in y over change in x, right? And so just to remind you of that here, all the way back. Change in y over change in x. That's our rise over our run, right? And so we can pick, again, either one of these to be our first coordinate pair. And in this case, I'm just going to go ahead and pick this one as 1 and this one as 2. So our -2, -3, that's going to be our x1, y1. And our 1, 4 is going to be our x2, y2. And again, just to make things very clear, highlighting is kind of helpful. So we have x1, -2, x2 is 1, and here. And then we have y1 is -3, y2 is 4. Those are found here. And then it's just a matter of plugging in. And the more you do this, you'll get a lot more comfortable with it. So y2, 4 minus y1, which is -3. Again, you should have a red flag when you see the negative number in a coordinate. So we have y2 minus y1, which is a negative 3. So we have a minus a negative 3. And then for the denominator, we have x2, which is 1, minus x1, which is negative 2. I just like to use parentheses so that way you don't get confused and think it's one long subtraction sign. You want to make sure you know you're subtracting a negative 3, which really means, when we simplify here, that we have 4 plus 3 and 1 plus 2. To finish off the simplifying, 4 plus 3 is 7, 1 plus 2 is 3, and we have our slope. So it's a lot of work to just get the slope. But now we have the slope, and we have 2 points. So how do we use point-slope form? Well, we can actually just go ahead and choose one of the points. It doesn't matter which one. So I'm going to choose just this second point here because there's no negatives, just to kind of make things easier. But I challenge you to choose the first point and double check my work, because we should get the same answer. It's a nice way just to show again how you have a lot of options. So let's take our point 1, 4 and our slope of 7/3 and go ahead and find our slope-intercept form. So again, slope 7/3. Our point is, what did we say, 1, 4? The one we chose? Yes. And so our other point becomes irrelevant. We know it's on the line, but all we need is 1 point on that line for point-slope form. The other point was just helpful to us for finding the slope, because we definitely need 2 points to do that. So now we return to our point-slope form that we know and love, but not as much as slope-intercept, right? And we plug away. So just as a reminder, this is x1, this is y1. We have y minus y1, which is 4. No need to worry about the double negatives. Slope is 7/3. And we have x minus x1, which is just 1. Again, we want to distribute over here on the right-hand side first. It's my preference, and then we'll worry about the 4 over here later. Go ahead and distribute. A highlighter would be nice once again. So we definitely don't want to forget about the sign in here. That's very important. Some people just distribute the 7/3 to the x and then to the 1 and then just put the sign in between. It's totally up to you. Just make sure you take care of that sign in some respect. So let's go ahead and work on this. Left-hand side comes down. I have 7/3 x times, or plus 7/3 times negative 1, which would give us negative 7/3, right? And then now all we have to do is finish this thing off. So we're going to bring the 4 over just like we did in the last example, very similar. And just because this is a fraction doesn't mean that we can't combine these. These are like terms because they're both constants. So again, we're left with y equals 7/3 x, and then this quantity, which we are going to do over here off to the side since it involves a fraction. So when we're adding two fractions together, it's really just easiest to go ahead and make this 4 into a fraction with a denominator of 3. So we have common denominators and can just do this a lot easier. So a nice little trick, again, that we can use is our divide by 1 trick that we used to make this into 4 divided by 1. And then another trick that we can use that will not change this at all is just by multiplying by 3/3. So at first glance it probably looks a little bit strange. Think about it, 4 over 1, we still have 4, and if we're multiplying by some number divided by itself, that's just 1. So 4 times 1 is still 4. So this entire thing here is just a sneaky little way to rewrite 4. And then when we multiply across, what you'll notice, we get 4 times 3, which is 12, and 1 times 3, which is just 3. And now we have common denominators here, which is really nice to work with. And this is just a sneaky way of writing 4. So that's kind of a neat little trick there that you can practice a little bit more. It takes a while to get used to, but it's certainly a nice way to think through things. Or you could just think, 12 divided by 3 is 4, and we want that denominator of 3. Whatever works. So then we have, I'm just going to kind of make some divisions over here. Negative 7/3 plus 4, which we know is equivalent to 12/3. And now it makes things a lot easier, right? So we have negative 7 plus 12, which should give us 5. So basically what we're doing is we're taking this negative sign, putting it in the numerator, and then adding it to this numerator. So we have negative 7 plus 12. And if this were a minus sign, we'd do minus 12, but in this case it's positive. And then we have that common denominator of 3. And so this all simplifies to 5/3. And I did that the long way, just kind of to really break down the process and hopefully make fractions seem a lot less scary to you, because they're really actually quite useful. And I used to really dislike them, but they're really quite awesome when you work with them a lot. And so there we have it. We are finally in slope-intercept form. Slope is 7/3, of course. There is our y-intercept. All that work, but we started with just 2 points. And so we've come a long way, certainly. And so we are finally in the form that we want. And so, as promised, to round things out today, we have a real-life situation that we're going to talk about. And when I had originally made this one, I realized it wasn't all that applicable and was kind of odd, so I kind of reworked it, and I think this one is a lot more believable and kind of shows the usefulness of linear equations in some respect. So we have Sally. She's in a cab that charges $2.50 per mile, plus a $5 fee charged to all customers regardless of however many miles they travel. So you're asked to create a linear equation that models this situation. Again, we get out of graphing, but I'm going to kind of draw a little graph here at the end just to show things, how things look. But let's think about this. So we're going to take our slope-intercept form, y equals mx plus b. And if we look at our variable x here, it's dependent on the slope, right? And another word for a variable is an unknown. So if we look back here, what do we not know? What are we not given? If we read it here again, the cab charges $2.50 per mile plus a fee charge regardless of the number of miles. Well, what we don't know is the number of miles, so that's going to be our unknown. That is going to be our unknown, so we're going to call that x. And just to make things really clear, x and y are just the common variable names that we use. But we can really use any variable, and it actually becomes really helpful in real-life situations. So in this case, let's call the number of miles traveled m, or actually mi. So that's the number of miles. So you always want to define your variables. And then our y variable here, you'll notice that when we graph, the y-axis is actually going to represent the price. So we can call that c, or cost, right? So let's put this all together. So we're going to replace our y variable with c for cost. The total cost of the trip is going to be our slope. I say that with air quotes because it doesn't really sound like a slope, but that is the price per mile. So when we see this little word per, that should remind us of multiplication. If it doesn't, it should now. So we are saying $2.50 charge for every mile, and we don't know how many of those miles. That's our variable, right? That's going to be our x. And so for each x, we know that the cost is going to be $2.50, so 2.5 times mi, or the number of miles. And then in addition to that, a very easy word to know what it means. I mean, plus means plus, right? 2.5 times the number of miles plus a $5 flat fee. So this fee is not dependent on the miles like the price is. This is just a price that's fixed no matter how many miles you go. And so this is our linear equation. But we're going to go a step further here just to show kind of what the graph would look like, just kind of like a sketch. So first of all, we're only going to draw our x and y axes because you would only want to have positive miles, right? And only have positive cash, right? You wouldn't be losing cash to the driver. I mean, you're giving the driver cash. But it just makes sense in this situation to have positive axes. And that's what you want to think about with real life situations. You are not going to not owe money when you get in a cab, right? You're going to owe something. So you want this axis to be positive. And same for the miles. You're going to travel some distance, even if it's very little, right? You're not going to travel negative distance. That just doesn't make sense. And so again, we've relabeled our x variable as miles. So this is going to represent the miles, this axis, and this axis is going to represent the cost. So you'll notice our y-intercept of 5, that's saying even if we go 0 miles, we still owe $5. So the least you're gonna have to pay on any trip is $5, even if you don't travel a bit, right? And if you travel a little bit, it's going to cost at least $5. That's our minimum. And then from there, it's going to go upward because we have a positive slope, right? Our slope here is positive. So basically what it's saying, the more miles we travel, the bigger our cost is going to be. This is kind of a nice visualization of this situation. And then if you were to go a little bit further with this, you could pick out a certain number of miles and tell what the cost is there very quickly, right? You just plug it in. And also you could determine a cost that you could pay and figure out how many miles you could go. So there's a lot you can do with this, and that's kind of where the real life application comes into play, and it's kind of neat to think about and work with. So I hope you've learned something today. Thanks for watching, and take care.